Well, good morning, everyone. Yes, I'd like to tell you about this, what I think is an exciting development as a scientist. This perhaps represents the culmination of a lot of the ability of science to deliver to the energy community, and in a very practical way. If I can, yes. This is to do with using forecasting to enhance the grid, the operations of the electricity grid, and enable more variable renewable energy onto the grid than would normally be the case. So I'm going to take you through in a logical fashion that why do we need the forecasting in the grid operations? More importantly, how does the energy market operate that requires this forecasting? And in the case of solar, we've got a precedent. We've actually done this exercise for wind. We've learned a lot, and we're trying to build on that for the case of solar. The solar has its particular challenges, and then I'll describe the project we're embarking on at the moment. So in the case of Australia, and I think this is probably the case for much of the world, if you look at the predictions for the energy mix into the future from the generation side, you'll see considerable changes. Here's some economic modelling CSIRO's done. This is based on putting a price on carbon. It's driving the energy mix with a price, and also a price on carbon, and also it has the maturing of various technologies and the economic curves for those. And when you put those together, you find that you transition to quite a lot of intermittent generation. So the little bracketed section there is a lot of wind and solar in various forms. And we see a lot of the fossil fuel-based systems dying away, particularly coal being replaced by gas and gas carbon capture and storage and the like, but there's this large component of intermittent energy in the mix, and that goes out to 2050. Firstly, about the Australian case, we are quite unique in that we have a single unified grid on the East Coast where most people live. Apologies to those I know from Western Australia here. But the connectivity, it's some 4,000 kilometres of grid. It's very long, and certainly it has challenges in the ends of the grid are quite thin, if you like, and often the renewable resources are on those edges of the grid. Now the size of the energy market is about 50 gigawatts. Maximum capacity, and the unique aspect of this is that there's a physical coupling between the energy market, that is the money side of things, and the physical operation of the grid, and that's coupled at 5 minutes, not day ahead, not 3 hours ahead, but every 5 minutes there's a resolution of the physical requirements, and then the money's attached to it. So it's a very demanding situation, and that exposes it in some ways to the variability more than you would normally think. Currently we have about, in that 50 gigawatts, we have about 2.5 gigawatts of wind and about 2 gigawatts of solar, mostly rooftop. By 2030, which is not that long away, we're forecasting that wind would grow to 10 gigawatts and solar PV will grow to 13 gigawatts. These are estimates from the system operator themselves. And so that is a very large installed capacity to handle within the market system. Now we've, in light of the growth in wind energy, particularly at the moment, we've actually had wind forecasting in that market system since 2008. And it's called the Australian Wind Energy Forecasting System, and I'll explain about that in a moment. Just to give you a little idea of the way an energy market or a energy system operates, we see here a typical plot of of demand over 3 hours, and the blue line is the predicted demand for this particular morning. But of course, you don't know exactly what's going on out there, who's turning what on and off, and what you end up is with the green line. And the difference between the prediction and the green line is taken up with what they call regulation services, or we call ancillary services. And there's a set of generators sitting there on standby that inject or actually withdraw power from the system. And no, we don't want that. And that regulation keeps things exactly in synchronicity, the frequency stable and so on. Now, if you don't have forecasting of any sort, the intermittent renewables appear as negative demand. So if you've got a rooftop panel supplying your appliances or whatever, that drops the demand you require from your household supply. And you just scale that up, and so you have a big wind farm is generating well. It will reduce the amount of other electricity required in the system from conventional sources. So in this case, renewables are treated, or variable renewables are treated as negative demand. So they are accounted for on the, theoretically, in the blue line. So really, if you've got a lot of variable renewables, you really need to know when they're participating in the generation side so that they can be taken off, they can be removed from the demand that needs to be satisfied by the conventional generators. If you don't do that, then that red line, which is the difference, the error, can grow larger than your available spinning reserve, which is what's there to compensate. And that's when the lights start to go out. Or what usually happens is they turn the wind farms off. So in our market, any generator larger than 30 megawatts has to participate in this system. And its output is actually, if you're a conventional coal power generator or gas, you're actually what they call scheduled into the market based on your price, and you're dispatched. You get an order to deliver your power, and they're given a target point to deliver to. So they're declared a winner in the bidding system, and you deliver, which is okay if you're a coal or gas station. You just turn the throttle up or down. But in the case of intermittent renewables, they do have a system called semi-dispatch where they recognise that there's no way you can tell a renewable resource to generate more, but they do have the ability to turn them down. So that's why it's called semi-schedule. So they can follow the fuel, if you like, the sun and the wind, but they can be constrained down. So there's a sort of a hysteresis there that has to be taken account of. Now, as I said, the market is a 5-minute market. This is very important because the forecast has to be ready basically within a minute of that 5-minute boundary. So that's quite demanding on short-term forecasting techniques. And depending on the ability and the rate of change of the generators, their bids are reassessed every 5 minutes, and they're told to go. So a big coal power station will bid in very low price, and they'll tend to just keep generating. They also, and 5-minute forecasts go out for about 2 hours. I'll put this up in a chart in a minute, but then there's another regime where they have a 30-minute forecast, which is forecasts out for a few days. And then they have, on top of that, they actually have an adequacy forecast that goes out for 2 years. So they actually cover, in various ways, 5 minutes to 2 years. So this is the challenge. We have to meet this enormous range of requirements. And this is not set up for renewables. This is the normal operation of the market. They want to know that there's enough power against the demand from every 5-minute block right through to annual changes that take into account maintenance and the growth of demand and so on. So the variable renewables, as I said, is treated as negative demand, and they're basically required to participate in this forecasting regime. And so we have to provide forecasts of the renewable generation on these time horizons, which are quite demanding. And I think it's most useful to lay them out in a table. So you can see for the first 2 hours, we need a 5-minute forecast. Whoops. We need a 5-minute forecast every 5 minutes of the mean production. Then we go to the next stage, which is a 30-minute forecast, updated every 30 minutes for up to 8.5 days. And there we require probabilities. And this is to look at the contingency on the network and how much reserve is required. We need P90s, P10s, as well as P50. So we need the extreme possibilities of delivery. So if you've got a wind forecasting scheme or a solar forecasting scheme, you actually need to provide a spread of probabilities, not just your estimate of the mean. Then we have a couple of what we normally base on climatology, a 30-minute time-resolved forecast out for 2 years. And really, in the case of renewables, that's heavily based on climatology. And because it, again, needs these probabilities, you have to look at the interannual variability. So when they're planning the adequacy of supply in the market for next spring, they have to know what the range of possibilities for wind and solar generation is on a seasonal basis, and you have to do that on a daily or even a half-hourly cycle, so they know the potential extremes that they have to cope with in a statistical sense. So I mentioned that we've had wind forecasting. Because wind was starting to cause problems and the spinning reserve was looking more and more inadequate, the grid operator, the Australian Energy Market Operator, AEMO as we call it, introduced a wind forecasting system through a public tender, and the successful system was the Anemos system, which some of you all know is produced by a European consortium, and it's actually been working extremely well. Now, one of the features of this is that it is a system which, on the left-hand side of this diagram, takes numerical weather predictions and online data from the power plants, the wind farms, and puts it into a data system which is available to for a range of techniques. Now, we need a range of techniques because we're covering this 5 minutes to 2 years. And these techniques plug in as modules. And so I know there's at least 6 modules running in the wind forecasting system at the moment. And so you're actually able to have a decision engine which decides a regime switching forecasting system where it can recognise the best system in those, not only in the time frame, but also the best system in that particular weather situation. The other features are that this system is a compulsory centralised forecasting system. So all the wind farms are forecast centrally, they don't have to do their own, and every generator over 30 megawatts is required to send in a 10-second data feed. So this is quite demanding if your system is in the middle of the desert. It will cope with up to 200 units, wind farms, and it's been operational since 2008. The other feature is it has a researcher access portal, which enables researchers to access the data 24 hours after the market has run, and you can get data out of the system. The data, the 5-minute data, and every 5-minute forecast set is kept for 7 years. It's because money's attached to it. They have to be able to resolve disputes. And if you got the forecast wrong, then there can be questions asked. And I know there's been some cases where producers have argued that the forecast was wrong and will sue you. But the data's all sitting there for 7 years. So it's a massive data system. And I'm told by the developers, who are from a company called Overspeed in Oldenburg, that your forecasting module is about 15% of the effort in getting the system to run. It's basically a massive data engine ingesting lots of real-time data feeds and producing the results in the form that the market requires. The performance of this system is very satisfactory as far as the market operator is concerned. Here are some accuracy figures on the bottom of the plot. This is going from 2008 through to the end of last year. The bottom line is the 5-minute ahead forecast, and we can see that's running at better than 2% accuracy, mean absolute error, normalised mean absolute error, I'm sorry. And then we go through the lines at the various times ahead, and the really wobbly one at the top is 6 days ahead. And the reason it wobbles is because as a new wind farm comes on board, the system has to learn. It's got a lot of neural network learning in it, and it has to adapt the whole system to a new plant, and it takes a little while to learn the characteristics of that plant. But in general, it's regarded as very good and very sufficient for the market operations. So that's quite a good success story and sets the benchmark for a solar forecasting effort. What we have embarked on in this project is to extend this wind forecasting system. Because it's modular, we were able to extend the data structures to take in the data feeds required for solar. So we just expand the NWP feeds. We require the SCADA feeds, the 10-second feeds from solar plants. And that just requires a broadening of the databases. And then the solar-specific forecasting techniques will merely plug into this system. So we can plug in and run them alongside the wind, and they just take the data they need out of the data engine. So it's what I'd call a modification rather than an add-on. And so we really need, what remains then is to define the solar-specific inputs and the solar-specific forecasting techniques. I'll just skip through this quickly. Australia is particularly well endowed with solar. Here's the DNI map for Australia. In the population centres of Sydney and Melbourne, on an annual basis, we may get 4 times the production of northern Germany, for example. So rooftop solar has been particularly successful. And as the subsidies have been withdrawn, we find that the installation rates have continued at a high rate. And we're seeing that people are able now to put on solar panels without a lot of subsidy. And so it continues to be a very favoured form of generation. Now, of course, we've seen over the last few days many of the challenges of solar prediction, and here's a couple of them. Obviously, clear sky days are pretty straightforward. High intermittency is a problem, especially on this 5-minute basis, and for the plant operators themselves, normally if you participate in this market, you're not allowed to change your plant at a rapid rate unless you declare an emergency. And apparently the predictions for large solar plants is that they will actually exceed some of these ramp rate limits imposed. Also, here's a plot of hemispheric solar radiation over a long period. You've got monthly variations in the high frequency part of that plot through to fairly significant interannual variability. So that has to be taken into account in this climatology part of the forecast. So you've got to capture all this variability in the statistics. Operationally, we've got a couple of major challenges. One is the way big plants respond to intermittent cloudiness, and you can see here the clouds passing over not a particularly large array. And then you've got the very big problem of how do you describe the behaviour of a city with rooftop and very little data availability. The plan for the project kicked off in January. We had originally hoped to have 3 phases funded. At the moment, we've only got phase 1 funded. Now, the way this works is that we have an engineering project which does all those data expansions I was talking about. That's a big job, expanding the system to take the solar. And the contractors from Germany will install some basic forecasting techniques. Underneath that, on the bottom box, is in the top R&D, there's a science program. And the hope is that after 2 years, the science, a lot of which we've been discussing this week, will be to a state where it can be considered for production engineering, and it's suitable for entering into this very rigorous environment with very tight deadlines and accuracy requirements. So there's 2 parallel parts to this project, and the idea is that would be a rolling process over the subsequent phases, that there would be engineering of the best science and another set of science done, and this would hopefully form a rolling program of improvements. And this is what's happened in the wind case. So just to summarise what is happening, this is the spectrum here of timings required. I haven't put the statistical basis, the 2-year horizon here. But what's going in, I'll just... phase 1 is basically doing engineering and some statistically based models. So short-term models are based on modified persistence, and then we go through, after a few hours, to the weather forecast adapted to predict the power station output. And the science will then try to bring in some of the more advanced techniques over the next 2 years, and that is sky imaging through cameras and satellite-based predictions of cloud motion, and some improved weather forecasting techniques as well. And so that's the science set that will hopefully produce some engineering candidates. The participants in the project, it's funded by the Australian Renewable Energy Agency, part funded, 50% funded, 50% by the participants. CSIRO is managing the project and doing some R&D. AEMO, the energy market operator, is commissioning the engineering, which is done through the company Overspeed. And Overspeed themselves have subcontractors within Germany providing some techniques. The Bureau of Meteorology, and I'll just put here what each is contributing in the science program. CSIRO is working on the sky camera work, and I'll show you a couple of examples in a moment. We're working on predicting high variability events. We've already seen a paper from Alberto yesterday on that. And we're starting on the problem of this distributed energy conversion model for a city. The Bureau of Meteorology is working on some improved cloud schemes and aerosol schemes for the NWP. NREL is providing a lot of expertise on all these aspects where they have experience. But for the Australian research community, the capacity building continues with the University of New South Wales working on satellite motion vectors and improved solar thermal energy conversion models. University of South Australia, and John Boland's here at this meeting, is working on some improved short-term statistical techniques for the first few minutes of the forecast horizon. I'll just skip through this to some of the issues. Here's an example of some of the science programs. Sky camera-based techniques have great promise for very short-term forecasting. The issues have been the algorithms. We have a group who's trying to build a system based on very cheap hardware. This is fisheye lens security cameras. And the idea is to use a whole bunch of these and triangulate the problem. There's been a number of presentations again. You can look this up. These techniques, not only are they able to provide forecasts for the first 15 or so minutes, but also there's a a keen interest in using them for controlling that ramp rate at say, a 1 or 2 minute basis, so that it's really a better citizen on the grid, if you like, because they actually get financially penalised for these rapid ramps. An example that's, we've seen this before, you predict the cloud amount, and you need some quality control. And basically the idea is to predict a blob of clouds, whether it's going to impact over the solar disk. So you have a lot of algorithms that try and track these clouds around the system, identify and track the clouds. Motion vectors from satellite images, fairly established technique, needs to be production engineered. Variability, I'll skip through a bit of this because Alberto showed a very good paper yesterday on this, but basically you're trying to predict when these days, if you have a day like this, you'd like to know when it's coming and have a flag for the system operator that there's going to be a lot of variability that needs fast spinning reserve. I'll skip through that again. It's been covered in other papers. The big problem is the upscaling problem for a city, where we have basically a data limitation where we don't know a lot. We might know how many units are out there, what the installed capacity is, but we have no idea which way they're pointing, whether they've got partial shading during the day, what panels they are, what efficiency they are, what temperature coefficient they are, whole range of things. And you've got to really do a big statistical exercise to even start to predict what a city will produce. So it's really a data problem to try and predict. But as you'll realise, that most of the generation is going to come from this area. There's a scattering of large plants being built, but generally it's the rooftop that's going to be the problem to predict. And there is techniques which Australian National University and ourselves are working on, where you try and look at real-time data from the inverters. And some of these are available through companies like SMA, who have a system of putting the inverter output on the web live. So it's going to be the major challenge of this, I think, is this trying to estimate what all the rooftop PV is doing. We have some reference stations, for example. These are high quality stations in our own backyard here, but down on the bottom left you'll see we've been instrumenting some schools, a lot of schools there's been a Solar for Schools program in Australia, and so there's an opportunity to have live data feeds from a selection of sites around the city to try and build a statistical view of what the city rooftop PV is doing. And then the last thing is really solar thermal is a complete another story, because solar thermal has potential to have a lot of non-linear transfer functions, a lot of storage, a lot of delays, and so that there's a program to look at the way this might be described in a live forecasting system. So the constraints are really, again, that we have to have a very rapid update system, and we can't pipe images around the system. We really have to have a lot of on-site work, which, for example, sky cameras would have to do their calculations on the plant side and then deliver simple results back to the central system, because we require rapid updates. And so the forecast systems really have to work within the constraints of this highly rigorously constrained system. So where are we at in conclusion? We commenced the project this January. The go live for the engineering is early next year, and the science has to produce a feasibility report that they're going to be able to meet these requirements by the end of this year. We have to nominate the candidates for engineering by February, and they have to produce a full cost benefit study, cost meaning what computational resources and so on will be required by the end of 2014, where we're going to put up a candidate for the next round funding by early 2015. So I hope that's given you an idea of some of the complexities of trying to get science into a real operational system. But I tell you, it's a very exciting thing to do. Thank you.